Now, radical chemistry is going to be one of our most common approaches to add a bromine to our molecule. Um, as we continue on with a lot of reactions, especially our substitution and elimination reactions, often we'll have a starting material that's going to have a really good leaving group. And bromine is a great example of a leaving group. So, knowing ways in which we can add bromine to our molecule um, are going to be a really good kind of like tool within our synthetic like toolbox of like reactions that we know. Because we can take a molecule, we can brominate it, and then do a subsequent reaction on it based on the stuff that we're going to learn in subsequent units. Now, the most common way in which we add bromines to a reaction is through a free radical chain reaction. This is actually some terminology that we see a lot in polymer chemistry, and we're going to do a real world applications about plastics and polymers and thinking about how we can actually use the same type of ideas to actually make plastics. And for these free radical reactions, there are generally three main steps, and this is a little bit different than a typical reaction. Normally, when, for example, like you do an acid-base reaction, if you have 1 mole of your acid, you add 1 mole of your base, and the reaction happens relatively quickly. In your free radical reactions, your radicals are super reactive and will combine with just about anything that they can. So if you have two radicals, they're going to come together to form a bond. And because of that, these reactions can be very uncontrolled. So what we'll do is we'll actually do this reaction little bit by little bit by little bit. We might only generate, let's say, like 2% or 5% of our entire molecules into radicals. That way, there's really dilute and they have a hard time actually coming together. Um, we'll make a little bit of our product, and in that process, make more radicals, and then keep going, just doing little bit by little bit by little bit to avoid a bunch of unwanted side reactions. So because of that, there are actually these three kind of fundamental steps that kind of happen within our bromination or just free radical reactions in general. The very first one is an initiation. An initiation is going to be how we generate our radicals. You'll have a compound that doesn't have any radicals. You'll expose it to a condition. Often it's going to be either driven by heat or light, and it's going to undergo what we call a homolytic bond cleavage. So homolytic now, generally, when we think about bonds breaking, we think of a heterolytic bond cleavage. So, a heterolytic bond cleavage is like what we think about an acid base, where like both electrons in that bond go to one side. In that case, your conjugate base. In a homolytic bond cleavage, this is an even sharing of electrons. So, if you have a generic bond that's just A going to B, and then this breaks down in some condition, a homolytic is one electron goes to A, one electron goes to B, and this would therefore create an A radical and a B radical. And this is what initiation is. It's a homolytic bond cleavage where we get multiple radicals that are generated. Now, once we get those radicals to generate, those radicals are going to be on whatever the initiator is. And an initiator is an external substance that we add to the reaction to undergo this reaction to generate radicals. And the very first thing we need to do is we need to have these initiators react with our starting material to be able to generate a radical on our starting material. And this is our first part of our propagation. And our propagation is where we start with one radical and then we end with one radical. So our reaction will continue. And our first step is going to be putting our radical on our starting material. And then the second part of our propagation is going to be forming our product. Now, when we run through that propagation, the very first time, you're only going to convert just like that 2 to 5% of your products into your starting materials into your products. So it's really important that you have this start with one radical, end with one radical. So this can then cycle again and again and again, and then just keep making more and more and more product as it goes along. Now, as I mentioned, radicals are super reactive, and there are a ton of events which can result in a loss of your reactive intermediate. And if all of your radicals die, then your reaction is over and you have really poor yields. So there are termination reactions where two radicals come together to form a bond. And these are often going to be a bunch of different side products that are going to be like mess that we have to remove. And that's going to be things that you're going to learn in organic lab, ways in which you can like remove a bunch of unwanted byproducts. And those are our kind of like three fundamental like stages of our reaction. We initiate or we generate radicals. We get a propagation where we go through and we get a bunch of our products to form, and then we have terminations, which are going to be loss of our radicals. Now, while there are these three major steps, regardless of kind of what our conditions are going to be, they're all going to be following these same like three fundamental steps and generating the same product. And here I actually have 5 different reaction arrows, and all of these will actually generate the exact same thing, adding a single bromine to our like most stable spot on our molecule. So if you see any of these arrows, whether it's the very first one, which is liquid bromine and light, or your second and third with your NBS, or your third and fourth with your AIBN and peroxides, all of these are going to make the exact same thing, just the way in which, for example, they initiate might be different. So if you look at any of these, or if you see any of these reaction arrows, these are all the exact same in terms of what they'll make in the end. There's definitely different pros and cons, and we'll kind of briefly talk about a lot of them. So the very first reaction that we'll see is going to be this one right here, a reaction where we use light and bromine. H nu is light, and Br2 is liquid bromine. Now, in most traditional organic chemistry textbooks, this is going to be the probably most common reaction that you'll see for your bromination, Br2 and light. It does work, but there are definitely some complicating factors. Liquid bromine is a pain to work with. It is a really dense liquid, and it is this like dark, dark, dark orange, almost like this like brown color. It looks very evil. It fumes, so it has like orange vapor or smoke that comes off of it, and it will oxidize or corrode a lot of things, including like metals. So if you store this in a cabinet that has like metal screws, for example, your metal screws will slowly turn into this like black tar and then like drip along the sides of like your cabinet. So there's definitely some storage and some safety issues associated with liquid bromine. Um, and it's also driven by light. So the generation or the initiation of your radicals is controlled externally by your light, which sometimes isn't always the easiest to control. So a lot of these reactions, you might like wrap your flask in aluminum foil to avoid generating too much radicals, and kind of like controlling how much light actually gets to your uh, reaction flask. Liquid bromine and light works, but in lab I won't use it unless I have to. The main one that I would typically use if I'm going to do a bromination are going to be the second group here, which we'll go ahead and show in blue. And these are going to be N-bromosuccinimide. The structure is down here, and we abbreviate that as NBS because N-bromosuccinimide is way too hard to write. In here, you have a bromine source and a radical source together. You can actually react this with either light or heat. Heat is shown by that delta or that triangle. And both light and heat can generate your radicals. The bond between this nitrogen and this bromine is going to be your reactive bond. So when you expose that to light or heat, this can undergo a homolytic bond cleavage, where one of your electrons go to the nitrogen, which is your succinimide, and then one goes to the bromine. This succinimide is actually a super stable radical because of the fact that radical can resonate into your carbonyls, both of your oxygens, so that can be spread across 5 different atoms, making it a longer lived radical, meaning it won't combine as quickly. And you also generate your bromine radical, so it's kind of a one-stop shop for everything. The other alternatives are going to be reactions that have an external initiator. So whether this is AIBN, which we'll show here in our green, or our peroxides shown here in our pink. Each of these will still use some bromine, and typically these are generated by heat. So AIBN is this structure below, and it's a really nice radical generator. It's probably one of the more common ones that you'll see. It has this nitrogen-nitrogen double bond in the middle, and the two bonds that are adjacent to that are your weakest ones. So when you heat it up to a specific temperature, that those will break down. This actually undergoes a double homolytic bond cleavage. So you'll get one side here and then one side here, which will generate your two equivalencies of your radical. And then your nitrogen actually becomes N2 gas, which is actually really nice because with it being N2 gas, it will actually bubble out of your reaction, and then you don't have any kind of like unwanted extra stuff. The radical that you actually generate is also a super stable radical. We see that's a tertiary spot. There's 3 different bonds around it, and that cyano is an electron withdrawing group, so it has a dipole associated with it, so it's pulling a bunch of electron density towards it. So you also get some extra inductive effect there. That gives you a really nice, stable, longer-lived radical, much like the succinimide. And these are going to be better than just your liquid bromines. Your typical liquid bromine, I guess I should maybe show that too, which is just your Br-Br bond. Under the presence of light, that can undergo a homolytic bond cleavage, where that splits and then makes 2 of your bromine radicals. Your last major class that we'll talk about in here are going to be our peroxides. And our peroxides are going to be structures that have the general form of something, oxygen, oxygen, something. And the main thing that we see here is this oxygen, 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 oxygen double bond. These oxygen-oxygen double bonds are not super stable. They break down really quickly through a homolytic bond cleavage, where you get your radicals to form on each of your oxygens. The simplest kind of our peroxide is just hydrogen peroxide. And that's where both of our R's are just H's. Hydrogen peroxide is something that you might even have in your like medicine cabinet at home. Typically, you'll see if you have hydrogen peroxide at home, it's generally in a opaque bottle. Normally, it's a like brown bottle where you can't get any light into it. And that's because we try to minimize the process of that homolytic bond cleavage. If you have a clear bottle, a bunch of light can get in and actually cause that splitting. So that's why you'll often see those opaque bottles for the hydrogen peroxide. And that's a really good radical generator. And that's why, like when you're young, if you're playing outside and you scraped your knee, your mom or dad might have put some hydrogen peroxide on your wound. Generates a bunch of radicals, which will react all over the place to try to kill any bacteria or stuff that gets in there. Nowadays, use of hydrogen peroxide is a little bit less because those radicals are kind of indiscriminate. It reacts with anything they see, so that actually does also attack some healthy tissue. Now, when we do a bunch of organic reactions, we'll often have like slightly different versions of radicals that are a little bit more soluble in organic solvents. A good example of this is BPO. This has this like benzene-like structure, and this is going to be one that's going to be a little bit nicer because of the fact that you get extra resonance and inductive stabilization, but functions the same. You have that oxygen-oxygen double bond in the, or oxygen-oxygen single bond in the middle, I should say, that will break into your 2 radicals, and those radicals can do a bunch of resonance. There's other versions of peroxides, but BPO and H2O2 or hydrogen peroxide are probably the 2 of the more common ones that you'll see. And regardless of which of these conditions you use, all of them are going to actually undergo the same general reaction, which is going to be putting a bromine on our molecule. So regardless if you see Br2 in light, NBS in light, NBS in heat, AIBN, Br2 in heat, BPO, Br2 in heat, hydrogen peroxide, Br2 in heat, all of those are the exact same, which is kind of nice in your case because you really just need to pull from any of those. Now we're going to get a bunch of practice in class actually like predicting the products, but I want to do a little bit of kind of like the steps in which we'll typically walk through. Step number one is in our starting molecule, which is often just going to be a simple alkane, to be honest. We're going to try to identify what is the most stable spot where we can put our radical. That does include a hydrogen because the initiator is going to react with our hydrogen to undergo a homolytic bond cleavage to get a radical on your starting material. So often we're going to say like, hey, do I have a benzylic spot or an allylic spot or a tertiary spot? What's going to be the most stable spot where I can put a radical? Now, if you are a benzylic or an allylic, especially allylic's going to be the ones that are going to have these little like asterisks next to them. There is a potential for a rearrangement to happen, and a rearrangement is going to be a resonance where you can go from, let's say, maybe like an allylic secondary to like an allylic tertiary, and end up making a more stable or kind of like unpredicted product. And then once you get that, once you know where that most stable radical is on your molecule, you're just going to put a bromine there. So the predicting the product is actually going to be relatively stable. The thing that's a little bit trickier is thinking about the fact that there are a bunch of different possible conditions we can use. And we can also think back to our last video when we think about resonance. Resonance can happen and sometimes give us some unexpected products. And we'll walk through some of those in class.